In this brief video, we'll talk a little bit about using geometry to compute the derivative of an inverse function. The theorem states that if f is differentiable at x, then f inverse is differentiable at f at x. This follows immediately just from the geometry. If we know that there is a derivative at a certain point, let's say that this point has coordinates x comma y, so if there's a tangent line to the curve y equals f at x at the point x comma y, that means that f is differentiable at x. And of course, the slope of this line is f prime of x. But the graph of f inverse is the same as the graph of f, just reflected through the line where y is equal to x. The point x comma y, when reflected through the graph y equals x, becomes the point y comma x. So here y is equal to f at x. If f has a derivative at x, that means we can draw a tangent line with slope f prime at x at the point x comma y. If we reflect all of this through y equals x, then we have a graph of a function, the inverse function, but we also have a tangent line, tangent at the point y comma x, where y is equal to f at x. But since we have a tangent line there, that means that the function f inverse has a derivative at y, but y is equal to f at x, so we're saying that f inverse is differentiable at f at x. The usual way to prove this is using the chain rule. We start with the definition of f inverse. F inverse undoes f. So x maps to f at x, but then f inverse sends that back to x. This is often called the cancellation rule. If we then differentiate both sides, we have the derivative with respect to x of a composition, f inverse of f at x, but this is equal to the derivative with respect to x of x. Of course, that's simply 1. On the left side, we differentiate the composition using the chain rule. It's the derivative of the outside, f inverse prime, times the derivative of the inside. Of course, the inside function stays inside, but then we multiply by the derivative of the inside. But of course, the derivative of f is just f prime. If you divide both sides by this f prime of x, then you end up with f inverse prime evaluated at f at x is equal to 1 over f prime of x. And this is really the result. We've established that if f prime exists at x, then f inverse prime exists at f at x. This isn't usually the way that we write it, so if we let y equals f at x, and therefore x is equal to f inverse of y, then we can rewrite this statement by taking this f at x and replacing it with y. So this f at x is the same as y, because y is equal to f at x. But we can solve this for x, and we write x is equal to f inverse of y. So this particular x we rewrite as f inverse of y, and this is the more usual way of writing the theorem. F inverse prime of y is equal to 1 over f prime at f inverse of y. And this is the more usual way of writing the formula. The advantage to using the chain rule approach is that in addition to proving that the function is differentiable, we also get a formula. But it turns out we can also get that formula by looking at the geometry. We know that there's a geometric relationship between the graph of f and the graph of f inverse. In particular, if you start with the graph of f, then the graph of f inverse is the same, but just reflected through this line, which is y equals x. So this line here is y equals x. And what that means is that if you start with a point over here, which has coordinates x comma y, if you reflect it through the line y equals x, then they swap roles. So this becomes the point y comma x. So that's why when we were looking at the derivative of f inverse, we were looking at it with an input of y. Okay, so what else do we know here? We know that we're trying to come up with the equation of a tangent line, essentially, because we know that the derivative of a function is the slope of the tangent line. And you can see just from looking at the graph that if this graph of f has a tangent line at a certain point, then the graph of f inverse also has a tangent line at a point which is corresponding to the original point. And again, we know how to find that point, because if you start with x comma y, that reflects through the line y equals x and gives you the point y comma x. So we have the point. If we want to figure out what the equation of this line is, we just need to figure out what the slope is. And we can do that using geometry. So let's just comment here. We know that the slope of this line, the slope of this tangent line, is equal to f prime at x. And if we look at this tangent line, we know that the slope of this line is f inverse prime at, and what is it at? It's at y. Because this point has coordinates y comma x. The input value is y. X is the output. The input value is y. So that means that this curve has a tangent line with slope f inverse prime at the input value, which is y. So this is the slope. We just want to find a formula for that. Well, we know the formula for that. We saw it on the previous slide, but we want to figure out what this formula is without using calculus. Let's make this picture a little bit bigger and go to the next slide. So here we have everything that we need. We have first the graph of f, and we know that the slope of this line, is f prime at x, because this point right here has coordinates x comma y. Now, how do you compute the slope of a line, generally speaking? It's the rise over run, or the difference of the y's over the difference of the x's. Well, this value right here is the difference of the x's. This value is the difference of the x's, and this value is the difference of the y's. So this is the difference of the y's. So the slope is f prime of x, but that's the difference of the y's over the difference of the x's. For whatever this x and y value are here, and this is x comma y, and then this is some new x comma y. So you just look at the rise over the run. Well, if you're reflecting this picture through y equals x, then what happens to everything over here? Well, the graph of f becomes the graph of f inverse, which you see here. The point x comma y becomes the point with coordinates y comma x. And the tangent line, which has slope f prime of x, becomes this tangent line, which has slope f inverse prime, and remember this is at y. This is at y because our input value is y. But what happens to this little triangle that we created here? Well, notice that this delta x corresponds to this little vertical distance here. So vertical lines become horizontal lines, and horizontal lines, or horizontal line segments, when you reflect through y equals x, become vertical line segments. So this length right here is delta x. And this vertical line segment becomes a horizontal line segment, so that's delta y. So the slope of this tangent line, well, it's going to be the rise over the run. Rise over run. But look at what the rise is. The rise is now delta x. So this is delta x over the run, but the run is delta y. Delta y. Now this shouldn't be as surprising as it might seem, because remember, when you reflect through the line y equals x, you swap the roles of the x's and the y's. So the difference of the x's becomes the difference of the y values, and the difference of the y's becomes the difference of the x values. So you end up with not delta y over delta x, but the reciprocal delta x over delta y. So this, in fact, is the reciprocal. It's 1 over f prime of x. So what does that tell us? F inverse prime at y is equal to 1 over f prime at x. But what is x? Well, x is this point right here. This point right here, that x is this x. So we want to get this in terms of the input y. So our y input is this y right here. So this y is that y. We want our formula in terms of y, and currently it's in terms of x, but there's a relationship between x and y. These are the two x's and y's right here. And what are they? Well, we know that this y is equal to f at x. That's from that right there. So another way of saying that is that x is equal to f inverse of y. Those are the same thing. These mean the same thing. So we can just take this value right here and just plug it in for this value of x right there. So let me just move this over a little bit. And now we can just take this x value and plug it right in there. And so we'll end up with 1 over f prime of x. But again, this x is f inverse of y. So this is just going to be f inverse of y. And this is exactly the same formula that we had on an earlier slide. But notice we didn't compute this using calculus, we computed it using geometry.